Hello and welcome back to Science for Sleep. Tonight, we're going to explore one of the most fascinating and mysterious questions in all of science. A question that sits quietly at the intersection of physics, biology, and the nature of reality itself. Why does the universe create life? Or more specifically, why does the universe create complex life when the laws of physics appear to push everything in the opposite direction? Because according to one of the most powerful principles in physics, the second law of thermodynamics, the universe should be steadily drifting toward disorder, toward randomness, toward chaos, toward a state scientists call maximum entropy. And yet here we are, you listening to this, me speaking to you, galaxies forming, stars igniting, planets assembling, oceans swirling, cells organizing themselves into incredibly intricate systems, brains evolving that can think, imagine, and wonder about the universe itself. All of this complexity seems to rise out of a universe whose rules appear to favor the opposite. So tonight, we're going to explore something scientists sometimes call the entropy paradox. If entropy is always increasing, why does complexity emerge at all? Why did simple particles eventually form atoms, then stars, then chemistry, then life, and eventually conscious minds? Is life simply a temporary ripple in the flow toward disorder? Or could life actually be something the universe naturally produces? Some physicists believe life may even be an inevitable consequence of the laws of physics. Others think life is an extraordinary cosmic accident. And some theories suggest something even more surprising, that life may actually be the universe's way of accelerating entropy, that living systems might exist because they help the universe reach thermodynamic equilibrium faster. But to understand this strange possibility, we first need to understand entropy itself, because entropy is often misunderstood. It's commonly described as disorder, but the truth is deeper than that. Entropy is really about the number of possible arrangements a system can have. Imagine a box filled with gas molecules. If all the molecules are clustered in one corner of the box, that's a very specific arrangement. But if the molecules spread out randomly throughout the entire box, there are vastly more possible ways they could be arranged. This more probable state is what we call higher entropy. Nature tends to move toward these states simply because they are statistically more likely. This idea was first formalized in the 19th century by physicists studying heat and energy. They discovered that energy tends to spread out. Heat flows from hot objects to cold ones. Gases expand. Structures break down. Over time, systems move toward equilibrium. And when scientists applied this principle to the entire universe, they realized something profound. The universe itself appears to be slowly drifting toward what is sometimes called heat death, a distant future where energy is evenly distributed everywhere. No stars, no gradients, no structure, just an enormous, quiet equilibrium. But if that's the direction the universe is heading, why did it ever develop structure in the first place? Why do galaxies exist? Why do stars form? Why do planets emerge? Why did chemistry become complex enough to produce life? And why did life become complex enough to produce minds? To understand the answer, we need to go all the way back to the beginning, to the moment when the universe first began expanding, the moment we call the Big Bang. Because strangely enough, the story of entropy and complexity actually begins with one of the lowest entropy states the universe has ever had. The early universe was incredibly hot, incredibly dense, but also surprisingly smooth and uniform. Matter and energy were distributed almost perfectly evenly across space. This might sound chaotic, but in thermodynamic terms, it was actually extremely ordered, which means the early universe had very low entropy. This is one of the great puzzles in cosmology. Why did the universe begin in such a special state? Physicist Roger Penrose calculated that the odds of the universe starting in such a low entropy configuration are almost unimaginably small. Roughly 1 part in 10 to the power of 10 to the power of 123. A number so large that writing it out would require more digits than there are atoms in the observable universe. And yet, it happened. The universe began in this incredibly unlikely configuration. And from that moment onward, entropy began to increase. But here's the strange part. As entropy increased, so did complexity. Gravity began pulling matter into clumps. Those clumps formed stars. Stars forged heavy elements in their cores. When stars exploded, they scattered those elements into space. Those elements formed planets. On at least one of those planets, chemistry became complicated enough to begin replicating itself. And life began. At first, life was simple. Single-celled organisms drifting in ancient oceans. But over billions of years, life became more complex. Cells joined together. Organisms evolved. Brains emerged. And eventually, conscious beings began asking questions about the universe. Which brings us back to the paradox. If entropy always increases, why does the universe produce islands of increasing complexity? Why does order appear locally while disorder grows globally? The key insight lies in something subtle but powerful. The second law of thermodynamics applies to closed systems. But many systems in the universe are open systems. They exchange energy with their surroundings. And when energy flows through a system, something remarkable can happen. Order can temporarily arise. Structures can form. Patterns can emerge. This is why hurricanes form in the atmosphere. Why snowflakes develop intricate patterns. Why convection cells appear in boiling water. These systems maintain their structure by dissipating energy. They exist because energy is flowing through them. Life, it turns out, may be a similar kind of phenomenon. A system that maintains its complexity by processing energy. Plants capture sunlight. Animals consume plants. Cells convert chemical energy into biological processes. At every step, energy flows. And entropy increases somewhere in the larger system. In other words, life does not violate the second law of thermodynamics. It actually depends on it. Life creates local order, while increasing entropy in the environment around it. Which raises a fascinating possibility. Maybe life isn't fighting entropy. Maybe life is actually helping entropy happen faster. Some physicists believe living systems may naturally emerge because they are efficient ways of dissipating energy. In this view, life is not an accident. It's a thermodynamic process, a way for the universe to spread energy more effectively. This idea is sometimes called the dissipation-driven adaptation theory, and it suggests that under the right conditions, matter may naturally organize itself into structures that dissipate energy more efficiently. Over time, those structures become more complex, more organized, more effective at processing energy, until eventually, they resemble something very much like life. But this is only one of many theories. Other scientists think the emergence of life is far more fragile. A delicate chain of improbable events. A cosmic lottery that may have happened only once. And still others propose more radical ideas. That life may be tied to the deep structure of the universe itself. That consciousness may play a role. Or that the universe may even have properties that favor the emergence of observers. These ideas touch on concepts like the anthropic principle, the fine-tuning problem, and even the possibility that the universe behaves like an information processing system. Tonight, we're going to explore all of these ideas. We'll examine what physics tells us about entropy, what biology reveals about the origin of life, what cosmology says about the universe's initial conditions, and what some of the most speculative theories suggest about the deeper nature of reality. By the end of this journey, you may find that the paradox itself begins to dissolve, because the universe may not be fighting entropy at all. Instead, the universe may be using entropy to build complexity, and life might be one of the most elegant consequences of that process. So settle in, relax, and let your mind wander gently through the strange and beautiful story of how a universe governed by disorder somehow created minds capable of understanding it. As we continue our exploration of the entropy paradox, something remarkable begins to emerge. At first, the universe appears to follow a very simple rule. Everything tends toward disorder. Energy spreads out. Structures decay. Stars burn out. Entropy increases. But when we step back and look more carefully at the universe as a whole, a more subtle pattern appears. Because the universe does not move toward disorder in a straight line. Instead, it often passes through stages of increasing complexity along the way. And that complexity is not random. It arises wherever energy flows through matter. To understand why this happens, we need to talk about something physicists call energy gradients. An energy gradient simply means that energy is unevenly distributed. One place has more energy than another. Hot next to cold. Dense next to empty. Bright next to dark. And whenever such differences exist, nature begins to move energy from where it is concentrated to where it is less concentrated. This movement of energy creates activity, motion, change, patterns. Think about a river flowing down a mountain. Water naturally moves downhill because gravity creates a difference in potential energy. And as the water flows, it forms complex structures, channels, eddies, currents. Over time, the landscape itself changes. Valleys form. Canyons deepen. All of this structure emerges simply because energy is flowing through a system. Now imagine something similar happening throughout the universe. Stars shine because nuclear fusion releases enormous amounts of energy. Planets receive that energy as sunlight. Atmospheres circulate heat. Oceans churn. Chemistry becomes active. And wherever this energy flows through matter, complexity begins to appear. This is why life is not evenly distributed throughout the universe. Life tends to appear in places where energy flows steadily but gently. Not too intense. Not too weak. Earth happens to sit in exactly such a region. Our planet receives a constant stream of energy from the sun. That energy flows through ecosystems, through plants, through animals, through oceans and weather systems. And every step of the way, energy is being transformed. Sunlight becomes chemical energy. Chemical energy becomes movement. Movement becomes heat. And through all of this, entropy increases. But along the way, something extraordinary happens. Life builds structures, cells, organs, brains, entire ecosystems. At first glance, these structures look like the opposite of entropy. They appear ordered, organized, deliberate. But in reality, life is constantly increasing entropy around it. Every living organism consumes energy and releases waste heat. Your own body is doing this right now. Every breath you take, every heartbeat, every electrical signal in your brain. All of it is part of a thermodynamic process. You maintain the order of your body by releasing energy into the environment. In other words, life creates local pockets of order, but it increases entropy globally. And this may be the key to understanding the paradox. Life is not resisting the second law of thermodynamics. Life is an expression of it. Some physicists believe this idea goes even deeper. They suggest that complex systems like life may naturally emerge because they are efficient ways of dissipating energy. Imagine energy flowing across the surface of a planet. At first, the energy may simply heat rocks and oceans. But if chemistry becomes complex enough, molecules begin to interact in new ways. Some molecules begin to replicate. Others begin to catalyze reactions. Eventually, networks of reactions form. Self-organizing chemical systems appear. Over time, these systems evolve into living organisms. Why? Because living systems may be better at processing energy gradients. They capture energy, transform it, spread it outward. From this perspective, life becomes part of the universe's natural strategy for distributing energy. Not a violation of physics, but a consequence of it. However, the story does not end there, because the emergence of life also raises deeper questions. Why did the universe begin in such a low entropy state in the first place? Why were the initial conditions so finely balanced? Some scientists believe this may simply be a brute fact about the universe. Others believe there may be deeper explanations. One possibility involves the anthropic principle. This idea suggests that we observe the universe the way it is because only certain kinds of universes allow observers to exist. If the universe had begun in a state of maximum entropy, there would be no stars, no planets, no chemistry, and no life to ask questions about it. So perhaps the universe had to begin in a very special configuration for observers to emerge. Another idea comes from cosmology. Some theories propose that our universe may be one of many. A vast multiverse where different universes begin with different conditions. In such a scenario, most universes might remain simple and empty. But a few may develop stars, planets, and life. And we naturally find ourselves in one of those rare environments. There are also more speculative possibilities. Some researchers explore the idea that the universe may behave like a kind of information system. In this view, physical processes are not only about energy and matter but also about information. Complex systems, including life, may represent ways in which the universe processes and organizes information over time. These ideas remain controversial, but they hint at something profound. The universe may be far richer and more creative than our earliest models suggested. Instead of a simple march toward disorder, the universe may pass through stages where complexity blossoms. Galaxies, stars, planets, life, consciousness, and perhaps even intelligence capable of shaping the future of the cosmos. From the perspective of entropy, all of this is temporary. Stars will eventually burn out. Galaxies will drift apart. The universe will continue expanding. Over unimaginable spans of time, energy will spread out more and more evenly. Eventually, the universe may approach thermodynamic equilibrium, a quiet cosmic stillness. But even if that distant future awaits, the path toward it has produced something extraordinary. A universe capable of generating complexity, capable of generating life, capable of generating minds. And perhaps that is part of the beauty of the entropy paradox. Entropy drives the arrow of time. It ensures that the universe changes. But those changes allow structure to form. And within those structures, something remarkable emerges. Awareness. The universe becomes capable of observing itself. Through galaxies and stars, the universe evolves matter. Through life, the universe evolves complexity. And through consciousness, the universe begins to understand its own origins. Which brings us back to the question we started with. Why does the universe create complex life against all odds? Perhaps the answer is not that life exists despite entropy, but that life exists because of it. Because energy flows through matter. Because gradients exist. Because the laws of physics allow structures to form along the way. In that sense, life may not be a cosmic accident. It may be a natural stage in the unfolding story of the universe. A brief but beautiful moment where matter organizes itself into living systems capable of wonder. And as you drift deeper into relaxation tonight, it may be comforting to remember something. You are not separate from this cosmic process. Every atom in your body was forged inside ancient stars. Every breath you take participates in the flow of energy that powers life on Earth. And every thought in your mind is part of the same universe that began nearly 14 billion years ago. A universe that, against all odds, created complexity, created life, and eventually created a mind capable of listening to this story. Thank you for spending this time with Science for Sleep. And as the universe continues its long journey through time and entropy, may your thoughts grow quiet, your breathing slow, and your mind gently drift into rest. Good night.